Okay, so we're gonna focus on solving differential equations using separation of variables. So we're gonna start with dy dx equals xy. Okay, so one of the things that should definitely spark to you that you need to use separation of variables here is the fact that you have both an x and a y in your differential equation. There's no way to do this without doing separation of variables. If I were to try to throw integrals on this thing right now, it would be crazy because I have two variables here, I'm not allowed to do that, and I have two differentials here, I'm not allowed to have that, particularly not a differential in a denominator. We never work with differentials in our denominator. So the first thing I need to do is fix it. So I'm going to take my dy dx equals xy, and I'm going to do separation of variables. I'm going to multiply both sides by dx. That's going to give me dy equals xy times dx. Multiply both sides by dx. And I'm going to divide by y. Okay, so these y's will divide out, and I'm going to have 1 over y dy. I don't want to write it as dy over y because that's often confusing. And I have this. Now, if I throw integrals on both sides of this, everything is great. Okay, so I'm going to do it up here. The integral of 1 over y dy is natural log of the absolute value of y. Okay, is equal to the integral of x dx is x squared over 2 plus c. Okay, and literally all this is I have two integrals that I'm going to do in sequence. Okay, I do one after the other, just like you've often done two integral problems as separate problems, but one after the other. Now we're doing them. I'm doing the left side integral, done, right side integral. I do want to remark real quickly that technically when I integrate this, I end up with natural log absolute value of y plus a constant is equal to the integral of x dx is x squared over 2 plus a constant. These are not the same constants, so one way that I can fix that is call this one constant 1 and this one constant 2. Okay, and then my next step, if I'm going to solve for y, right, if I have a dy over dx, which is what I started with, I had a dy over dx, okay, I want to solve for y. So the very first thing I would do with this would be to subtract these constants, combine constants. So this goes away, and I have a constant minus a constant, which is just going to give me a new constant. I don't know what its name is. So that's why I just put a single constant on the right side, on the side of the variable that I'm not trying to solve for. Again, dy dx means I solve for y. If I had a dy dt, I'd be solving for y. If I have a dp dt, I solve for p, and so on. Okay, so you always solve for the variable that's in the numerator of your derivative quotient. Okay, all right, so I didn't say, but I want to find a general solution to this, meaning solve for y here. So in order to solve for y at this point, to get rid of natural log, I need to exponentiate both sides. So I'm going to e both sides. I have e to the natural log of absolute value of y is equal to e to the x squared over 2 plus c. Okay, you e both sides. You don't e pieces, you e sides. So that's why it's e to the natural log y and e to the x squared over 2 plus c. Okay. E and natural log love each other, and so long as there's nothing in between them, they're going to run off together, they're gone. So I'm just going to get a y here. Okay, it's okay to lose the absolute values because of what's coming, because I have this crap here. It's e to a power. E to a power cannot be negative, right? It's e to the x squared over 2 plus c. All of that crap is in the exponent. Okay, I do want to simplify that. Let's make a little note. That if I have, for example, x squared times x cubed, I am going to keep the base the same and I add the exponents, right? And that's how I would get x to the 5th. A little algebra 1 refresher. But that means I can go backwards. So if x squared times x cubed is equal to x to the 2 plus 3, then I should also be able to go in the opposite direction and say that x to the 2 plus 3 is equal to x squared times x cubed, all right? And I'm going to use that up here. And I'm going to say that y is equal to e to the x squared over 2 times e to the c. Right? That's the principle I just used. So if I multiply these back, I'm going to add the exponents. So now this is e, which is just a number. It's 2.7 something, to a constant power. So I'm taking a constant and raising it to a constant power. It's going to give me a new constant. And I'm not going to track different constant numbers, constant 1, constant 2, constant 3, constant 4. I'm just going to call it a constant. And so then my answer is going to be y equals ce to the x squared over 2. Okay, and that is my general solution to this problem. Okay, so we're going to do another one. We're going to find the general solution to y prime equals x squared. All right, I was lazy reading that. It says y times y prime equals x squared. Personally, I hate anytime there's a y prime in my Diff EQ. I want to see my differentials so I can do separation of variables. So I'm going to rewrite this immediately as y times dy over dx equals x squared. Okay, and it's a quick separation of variables now that I see it this way. I'm just going to multiply both sides by dx. So I have y times dy equals x squared times dx. All right, and this is perfect form for integrals. I can throw integral signs on both of these, and they'll be peachy keen. So the first integral, I'm going to have the antiderivative of y dy is going to be y squared over 2. Okay, is equal to, I'm going to only add the plus c on the side of the independent variable. So the antiderivative of x squared is x cubed over 3 plus c. Okay, and I want to find a general solution, so I need to solve for y. So I'm going to first multiply by 2. I get y squared is equal to 2, I'm going to write it as 2/3 x cubed plus, now I'm doing twice a constant. I don't need to write twice a constant. I can just say, oh, a constant times 2 is a new constant. I don't need to track C1, C2. I'm just understanding it's not the same constant. It's not that the constant isn't affected. It's that I don't know what it is yet. And to call it twice a constant is silly. I could just say, oh, it's still a constant. Okay, now I'm going to solve for y. I'll do it up here. I'm going to get y is equal to, just remember when you're taking square roots, it's plus or minus the square root. So it's plus or minus the square root of both sides. So 2/3 x cubed plus c. Okay, square root of the sides, not the pieces. Okay, we're going to use the same differential equation, find the particular solution to y prime equals x squared through a specific point this time. And because of that square root thing, it's kind of an interesting situation. So right now I said y is equal to plus or minus the square root of 2/3 x cubed plus c. Looks better, right? So now I can take that solution and I can throw in these points and solve for c. Okay, so if I throw in a -3 here for my y and a 0 for my x, okay, the question is, what sign do I throw out front? Okay, and the only way to get a negative out of a square root is to throw a negative in front of the square root. So that's what I got to do. So it can't be plus or minus anymore for a particular solution. Particular means one solution. Plus or minus is options. So I need to decide if it's positive or negative, and it's really going to be by here. Okay, so if I had said through the point 0, 3, 0, positive 3, I would choose a positive square root, but because I said 0, -3, I need that negative in front of the square root. So I'm going to have -3 is equal to negative the square root of 0 cubed is just 0 times 2/3 is still 0, so c. Okay, I could divide both by a negative. I get 3 equals square root of c. And then to undo square root, I want to square both sides. So c would equal 9. And just double check that square root of 9 is 3. We're good. And now I'm going to go back and rewrite my function. So here's my general format. I decided that the square root should be negative. So negative the square root of, and it's going to be 2/3 x cubed. And I just found that c was 9. Okay. You're going to see solving some of these differential equations that sometimes you need a u-sub, just like solving a normal integral. Sometimes you need a u-sub. Actually, often you need a u-sub. Most of the time, we're going to end up having composites in some way or another that require u-subs. So watch out for them. Do your u-subs on the side. So you might need one on the left and one on the right. You never know. Okay, so we're going to find the general solution to this crazy mother function. It's the square root of 4 minus x squared over x times e to the negative y times dy dx equals 2. All right, so you need to break this apart algebraically. You need to get everything x over to the right side. So I'm going to multiply by dx. I'm going to divide by this fraction or multiply by its reciprocal. So what that's going to end up leaving me with is I'll end up with an e to the negative y and a dy on the left. That's what I want to keep there. So that stays, that stays. The dx I'm multiplying over. The 2 is just going to hang out for me, right? And I'm going to multiply by the reciprocal of that fraction, this fraction. So I'm going to have 2x over the square root of 4 minus x squared dx. Okay, and that's what it should look like with separation of variables. Make sure that all of that makes sense to you. That's just algebra, no calculus. All right, once you get to this point, you're totally good to throw integrals on both sides of this now. All right, if you look at both sides of this, I have composite functions on both sides. I have the integral of e to the negative y That's a composite. I have, on the right side, I have 2x over the square root of 4 minus x squared. That's not only a composite, it's also a quotient. Okay, and just be mindful that what you have here is an opportunity to not do just one u sub, but you get to do two separate integrals with two separate u subs, and it's like Christmas. You're welcome. Okay, so I'm going to do each one separately, and I'm kind of going to do it on the sidelines. So for the integral of e to the negative y, I'm going to do a u sub. A u is going to be the exponent. U is going to be negative y. Du is then going to be negative dy. So my new integral is going to become the integral of e to the u. And my dy is going to become a negative du. And this is going to give me negative e to the u. Okay, I'm doing that on the side. So for this side, my left side, my answer is negative e to the negative y. Okay. On my other side, I also need a u sub. Okay. So I'm going to do this over here. I'm going to let u be the inside of the composite. So I'm going to have u is equal to the square, not the square root, but the stuff inside the square root. U equals 4 minus x squared. Du then would be negative 2x dx. Okay, I don't have a negative 2x dx. I have a regular x dx. I'm going to throw a negative there too. So I'm going to have the integral of, and it's 1 over the square root of u, right? The square root of u is in the denominator. So it's going to be u to the negative 1/2, because I know I can't integrate square roots. My 2x dx becomes a negative du. I'm going to integrate this. I'm going to have negative. The antiderivative u to the negative 1/2 is going to be increased by 1, so u to the positive 1/2. Divide by 1/2 or times 2. Okay, and now I can throw it back in. So it's gonna show back up as negative 2 times 1/2 is square root. So square root of u is really 4 minus x squared. And this is where I need my plus c. Okay, I want to just take a second to just notice that I did both of my u substitutions on the sidelines. I cannot write that this stuff here is equal to this stuff here. They're not. They're totally different u's representing totally different things for totally different integrals. So I do them on the sidelines. They do not get caught up. Like, I'm not going to see that stuff in the body of the work. I'm not going to see the integral of, negative the integral of e to the u du is equal to negative the integral of u to the negative 1/2 du. You don't throw those together. You do them on the sidelines. And then you come back once you know what your answer should look like. Okay, so I want to solve this for y. And when you have e to a power, your instinct is to get rid of the e, and you want to get the exponent out of the exponent. You would take the log of it. But if I take the log of it right now, just to see what that would look like, there is something literally getting in between the natural log and the e, which means I cannot do it yet. Okay, again, for e and natural log to go and run off together, there needs to be literally nothing in between them. So here there's a negative sign in between them. I need to resolve that first, and then I can take the natural log of it. Okay, so I'm going to divide by that negative. I'll have e to the negative y is equal to 2 times the square root of 4 minus x squared plus c. Okay, at this juncture, if I try to take the natural log of both sides, I take a natural log of sides, not pieces. Same thing, square root of sides, not pieces. i.e. sides, not pieces. You're changing sides. Okay, so natural log of this whole stupid thing in here. Okay, and natural log and e love each other, so they run off together. So I'll have negative y is equal to natural log of all this crap, 2 times the square root of 4 minus x squared, plus c. Okay, inside those parentheses, inside the log. And then the last thing is just to get rid of this negative sign. And I'm going to be a little bit brief with it and use the magic of the whiteboard to get rid of it here and throw it in here. And that is my stupid, ugly answer, and we're going to call it a day. I want you guys to be careful with how much you bring over when you do separation of variables. Okay, for example, let me show you the difference between two different problems. Okay, so it's just for you to be aware of whether you're making your life harder or easier when you choose to bring over. So I want you guys to look at dy dx equals x over 2y versus dy dx equals 3y. Okay, if I do separation of variables with this first one, my instinct is to do almost like cross multiply by the 2y, multiply by the x. I'd end up with 2y dy equals x dx, and this is going to work out nicely for me if I do general solutions. So if I integrate this, the integral of 2y dy is beautiful. It's y squared. equals, the antiderivative of x is x squared over 2 plus c. Okay, doing my general solution for y, it's real easy at this point. I do y equals plus or minus the square root of x squared over 2 plus c. Okay, square root of the entire side. I cannot emphasize that enough to you guys. Okay, and that worked out great. I brought over the whole thing and it was great. Okay, on the second problem, if I bring over all of that 3y, okay, first of all, I'm going to multiply by the dx first, just so you can see what that's going to look like. So dy is going to equal 3y times dx. Okay, and usually our next step is, I'll divide it by 3y. So I would end up, if I divide both sides by 3y, right, they're going to divide out over here. And this side I'm going to write as 1 over 3y dy equals dx. Okay, now what number is really here is a 1, right? I'm not seeing it, but that's what we keep saying is there. I'm ready to throw integrals on both sides of this. So when I do that, this is the antiderivative. I'm going to do this right side first. I know it's not usually what you do, but it doesn't matter which side you do first as long as you get them both done. The integral of 1 dx is just an x plus a c. When I go to integrate this, I have options now, okay? So my integral of 1 over 3y dy, I can do, and this is similar to one of those problems on that U sub worksheet, can do it two ways. I can either factor out the 1/3 and do it 1/3 times the integral of 1 over y dy, which becomes 1/3 times the natural log of the absolute value of y. And now if I have that, and the other side of it was an x plus c, now I have to multiply by 3, which is like, why did I bring that 3 over now if I just have to bring the 3 back over to the other side? So that's what I'm going to have to do. I have to bring it back over to the other side. I'm going to have natural log of absolute value of y. Again, and let's just talk about why I need to do that. If I were to try to exponentiate both sides on that, and let me back up even more than that. Looking at this line, okay, what I want to do is I want to solve for y. And I have a natural log of y. To undo that natural log, I need to exponentiate both sides. But if I try to exponentiate both sides here, I have e to the stuff, but that 1/3 is literally between the e and the natural log. They cannot be together if that's what's happening. So before I can do that, okay, what I need to do is I need to get rid of that 3. So I brought it to the left, but now I have to bring it right back to the right. And I'm going to have natural log of absolute value of y is equal to, 3x plus 3 times a constant is still just a new constant. And now I'm at the point where I can e that side. Okay, so I'd have e to the natural log of absolute value of y would equal e to the 3x plus c. Okay, e and natural log love each other. They can be together now. I'm going to get y is equal to, and e to the 3x plus c, I was explaining to you guys before, I can write that as e to the 3x times e to the c. Okay, I do not need to see that step, but that's what's happening here. This thing is a new constant, and you are more than welcome to jump right into this from here to here. I don't need to see this step. Okay, so that's what it looks like when I do that. My other option to this integral is to do a u substitution. And if I do a u equals a 3y and a du equals a 3dy, and I'd have to go through the whole thing, and I don't want to do it because it's a giant waste of time. Okay. Versus if I go back to this one, and instead of bringing over that 3y, I just say, okay, I have dy dx equals 3y. What I'm going to do is I'm going to just move the y. I'm not going to move the 3. So when I multiply by my dx, I'll have dy is equal to 3y dx. I'm only going to divide out by the y. So I'm going to have 1 over y dy is equal to 3 dx. And again, I'm doing this because when I moved the 3, I just had to move the 3 back. So what's the point of moving it to the left side just to move it back to the right side when I could just leave it on the right side? And when I do this, I don't need to struggle with this integral. It's no longer a composite that either needs to be simplified or requires a u sub. I just get to integrate it. And the antiderivative of 1 over y dy is natural log of absolute value of y. The antiderivative of 3 dx is 3x plus c. And now I can e both sides. So I'm going to have a y equals ce to the 3x. Okay, so I just want you to don't do it blindly that you're just bringing over random stuff without putting thought into it. You need to kind of assess what's going to be helpful, what's going to be unhelpful, or if you bring it over and realize, that was silly, then recognize it and go back and put it back to where it came from. Okay, but other times it's helpful to move the coefficients. So you kind of have to judge based on what's in front of you.